So, hello, a very good morning to all, and welcome to my class. So, this is the second lecture of this chapter, right? So, from today, we are going to discuss the remaining part of this chapter, that is the transition element and the coordination compound. So, we are going to discuss today some remaining portion of block elements as well as coordination compounds. And at the last, we are going to solve some PYQ questions that were coming in your advanced exam, right? So, let's start with the today's session. We left this class at the F block element, right? We completed D block transition element, and now we are left with the F block elements, right? So, what is this F block element basically? So, let's see quickly what is F block element. So, basically, the element in which the last electron enter into f orbital of the anti-penultimate cell, or we say inner to the penultimate cell, right? Because as we observe in d block element, the last electron enter into the penultimate cell. So in case of f orbital, the last electron enter into the anti-penultimate cell, or we say inner to the penultimate cell, that is n minus 2 shell, are called f block elements. So these are called f block elements. Since these constituent transition series within transition series and the last electron occupy the anti-penultimate cell, these are named as inner transition elements. So always remember this thing, because transition element in which the last electron enter into the penultimate cell. So in this, the last electron enter into the anti-penultimate cell, that is the last to the penultimate cell. Okay, so we can say that block element is the inner transition element, right? So we can define as the inner transition element. Okay, let's look some the general feature of this block elements. Like these all have been kept in the third group, or we say 13th group, third group or group 3 of the periodic table. In this element, both the D and F subshell are incomplete, right? So in this element, both the D and F subshell are totally incomplete. Now, what are the general electronic configuration of these elements? So general electronic configuration of these elements be like n minus 2 f1 to 14 and ns1 to 2, or we say n minus 1 d0 to 1 ns2, right? So these are the general outer electronic configuration of this element we can classify, right? Now, depending upon the nature of the f orbital of the anti-penultimate cell in which the differentiating electron enters, these are further divided into two series, that are 4f and 5f series, right? So depending upon the nature of the f orbital of the anti-penultimate shell in which the differentiating electron enters, these are further divided into the two series, like the 3D series, like they have a 3D, 4D, 5D and sub 6D series, which is incompleted one. Like also F block is further classified into the two series, that is 4F and 5F series, right? So they are the general electronic configuration of the 4F series, like Xz, Xenon, 4F 1 to 14, D either 0 or 1 and 6s2. So these are the general electronic configuration of these elements, right? For example, the first element of the 4F series is cerium. So cerium having the atomic number 58. Next is parasodium having atomic number 59. Neodymium having atomic number 60. Promethium, samarium, europium. So these all are the atomic number according to this, right? So as you observe in the cerium having atomic number 4f2 and 5d0, and this will be 6s2, right? So just remember europium out of these, because europium having half filled electronic configuration, which makes them very stable, right? So if I'm talking about the electronic configuration of europium, it having electronic configuration Xz4f7 5d0 and 6s2, right? So this how we can write the electronic configuration of the 4f series of the f block element, right? Okay, now these are the basically the atomic and the ionic radii. So in 4s series, as the atomic number increases from lanthanum to deuterium, right? So as in 4s series, as the atomic number increases from lanthanum to deuterium, the atomic and ionic radii decreases gradually, because we know that whenever we move from left to right, due to increase in the nuclear charge, size always decreases. Okay. Now, this is this decrease in the atomic and the ionic size from lanthanum, that is atomic number 57, to the lutetium, that is atomic number 71, is unique feature and known as lanthanide contraction. So this is basically known as the lanthanide contraction. So this contraction is attributed to imperfect shielding of electron of f orbital. So always remember this point. This contraction is attributed to the imperfect shielding of electron. Due to this contribution, that is from 57 to 71, suddenly 14 elements are added as known as lanthanide contraction. Due to this contraction is attributed imperfect shielding of electron of d and f orbital. It is even less than the shielding shown by the d electrons, right? So it having very low shielding effect and even less than the shielding shown by the d electron. Now, as a result, what happening? As a result of the lanthanide contraction, the normal increase in the size from scandium to Y to La disappear after the lanthanide. And the pair of the elements such as zirconium and HF, Nb and Ta, Mo and W have nearly same size, right? So their size suddenly, in place of increasing in the size, their size remain almost constant. The properties of this element are very similar, and the similarity in property with this pair makes separation of the lanthanoid very difficult. So always remember this, the separation of a lanthanoid is very difficult. Why? Because their size are identical, they are on same size, right? Now, due to lanthanide contraction, the element of 5D and 4D series resemble each other much more closely than do the element of the 4D and 3D series, right? So due to the lanthanide contraction, the element of 5D and 4D series resemble each other much more closely than do the element of the 4D and the 3D series. So remember this. So this is due to the lanthanide contraction, right? The element of the 5D and 4D series resemble each other much more closely than do the element of the 4D and the 3D series, right? Okay, so let's talk about the oxidation state. So what is oxidation state basically? So all of them show variable valency or oxidation state. However, +3 oxidation state is the most stable one, right? So all of them show variable valency or oxidation state. However, +3 oxidation state is the most stable one. Some of these elements also exhibit +2 and +4 oxidation state along with +3 oxidation state, right? So some of these elements also exhibit +2 and +4 oxidation state along with the +3 oxidation state. Higher oxidation state are not possible because there is a large energy gap between 4F and 5D subshell. So always remember this, +3 oxidation state is the most stable one, and some of these elements also exhibit +2 and +4 oxidation state with +3 oxidation state as well, right? So the higher oxidation state in this case is not possible, like +7, +8 is not possible because there is a large energy gap between 4F and 5D subshell. So it is very difficult for electron to lose the electron from both of these two shell cells, right? So it is very impossible to show large number of oxidation state. Now, following a stable ion also exists as like 4F0, lanthanum in +3 state they are quite stable because they have a 4F0 electronic configuration. Similar deuterium that is in +2 oxidation state, GD in +3 and TB in +4. They all having 4F7 electronic configuration, which is quite stable. Similar YB +2 and LUE +3, they all having 4F14 electronic configuration. So always remember, whether it's in case of D block or F block, in case of D block as well, D0, D5, and D10. These three are the most stable state. Similar in the F0, F7, and F14. These three are the most stable state, right? So these all are the important oxidation state shown by the F block element. Now, if I'm talking about the color, so many trivalent lanthanide ion are colored in both solid state as well as in aqueous solution, right? And not shown by the lanthanum or cerium or GD+3 because they do not have any unpaired number of electrons. So the many trivalent the lanthanide ions which possess +3 oxidation state are basically colored in both solid state as well as in aqueous solution, but not shown by the La plus, cerium plus, GD plus, YB plus, lutetium plus, right? So the color of these ions is because of the FF transition, just like the DD transition. In this case, FF transition occurs due to the presence of partially filled F orbital. Now, Ce+4 is an orange red, like 4F0 is isoelectronic with La+3. Always remember Ce+4 is an orange red, while 4F0 is isoelectronic with the La+3. YB+2 is a yellow in color, like 4F14 isoelectronic with the Lu+3. So these are some resemble, right? Now, so what is the magnetic property? How will you calculate the magnetic property basically? So except cerium +4 and YB+3 and Lu+3, all other lanthanide ions are paramagnetic, right? So except cerium +3, YB+3 and Lu+3, all other lanthanide ions are paramagnetic in nature. However, the point of difference from the transition element is that here both spin as well as orbital moment give contribution. So the point of difference from transition metal is that both spin as well as orbital moment give us the contribution. Like if you want to calculate the magnetic moment, like in case of d block element, you observe one important thing here, where we only consider about the orbital moment, right? But here both spin as well as the orbital moment give the contribution. So how will you calculate the basically the magnetic moment? So we can calculate magnetic moment like 4s plus 1 and l plus 1, where basically s represent the spin as well as the l represent the orbital moment, right? So this is the formula that we use to calculate the this is the formula that we use to calculate the magnetic moment, right? So the paramagnetism increases to maximum in neodymium, that is Nd, having atomic number 60. Now, these are there are the general reaction which can be summarized as basically lanthanides show the reaction similar to the aluminium, right? We know that aluminium having plus 3 oxidation state. So just like aluminium plus 3 oxidation state, this lanthanide, all lanthanides show a reaction similar to the aluminum in plus 3 oxidation state, right? For example, when they react with acid, we know that whenever the aluminum react with acid, it always form AlCl3 and the liberation of hydrogen gas takes place. So this is true in case of lanthanide as well, right? Similar when they react with the halogen, aluminum react with the halogen to form AlX3, right? Here also they will form AX3. So this is also very much similar to this. When the aluminium react with water, they form AlOH3 plus H2O, just like lanthanide, right? Now, when they react with the carbon, they form carbide. So the similar cases when they react with A2, we know that aluminium react with O2 to form what? We know that the aluminium 3O2 having 2, so they form Al2O3. So just like that, lanthanide also form A2O3. Heated with sulfur, they form A2S3, and heated with nitride, they form An. So where A is the lanthanide. So just remember the reaction of the lanthanide is very much similar to the aluminium. So whenever some reaction is coming, just remember the what the reaction that occur in the aluminium. So if you know this thing, then you can easily write the reaction of the lanthanide with the different acids or halogen or sulfur or oxygen or anything, right? So I hope this is clear to you. Now, what are the main differences between the lanthanide and actinide? So how will you differentiate these two? So the first difference is B side plus 3 oxidation state. They show plus 2 and plus 4 oxidation state only in the few cases, right? So beside the plus 3 oxidation state, lanthanide can also show plus 2 and plus 4 oxidation state only in a few cases. Now, what about actinides? So B side plus 3 oxidation state, they show higher states of like plus 4, plus 5, plus 6, and plus 7 also. Right. Now, lanthanide compound are less basic. So if I'm talking about the basic characters, then lanthanide compound are less basic. Where I'm talking about the actinide compound, so actinide compound are more basic. Okay. Now, they have a less tendency towards the complex formation. So they have a very less tendency towards the complex formation, where they have a greater tendency towards the complex formation. So always remember they have a greater tendency towards the complex formation. Now, most of their ions are colorless. So most of their ions are actually colorless. Now, if I'm talking about the actinoids, most of their ions are colored. Okay, so most of their ions are colorless and most of their ions are colored in terms of actinide. Now, except promethium, they are non-radioactive. So except promethium, they all are non-radioactive. Where actinides, they are radioactive. So all the elements belong to the actinide series, they all are radioactive. Their magnetic properties can be explained easily. Their magnetic properties cannot be explained easily as they are more complex, right? So these are some major differences between these two, right? Now, we are going to discuss some questions after some time. Let's cover the entire topic, then we'll come to this topic, right? So let's study about the coordination compound. That what we are going to study in the coordination compound. Okay. So basically, what is coordination compound? So these are the chemical compound that consist of a metal atom or ion surrounded by the anion neutral molecule or sometimes positive molecules known as ligand through a coordinate bond. So basically, coordination compound is the chemistry of the metal ligand bond, right? So these are the chemical compound that consist of a metal atom or ion surrounded by the ligand. Now, we can classify double salt and complex compound as, because what is double salt? So basically the compound which lose their identity in the solution, in aqueous solution, these compound break down into the simpler ion, thus exhibit the properties of their constituents. An aqueous solution of carnallite, KCl, MgCl2, XH2O shows the properties of these. So basically double salts are those salts which lose their identity in the solution. So basically the salt which treated in aqueous, or when they dissolve in aqueous, they lose their identity. It means they will give different ions, right? So these compounds break into the simpler ions, thus exhibit the property of their constituents. Like aqueous solution of carnallite give us the potassium plus magnesium 2 plus chlorine into simpler ion. Such compound which lose their identity is called our double salts. Always remember this. They only exist in the crystalline state. Some other example of double salts are potassium and the Mohr salt. As we see, K2SO4Al2SO4 thrice, 24H2O, and Mohr salt FeSO4 ammonium sulfate, FeSO4 ammonium sulfate dot 6H2O. So always remember this, right? I hope this is clear to you. Good. Okay, so this is all about the double salt. So example of double salts are carnallite, potassium, and the Mohr salt. Now, what is complex compound that we are going to study in this chapter? What do you mean by this complex compound? So compound which retain their identity in the solution. So basically those compound which retain their identity in the solution, these compound do not furnish all simple ion, but instead give more complex ion having complicated structure. So compound which retain their identity, right? First point is compound which retain their identity in the solution. And next in aqueous solution, these compounds do not furnish all simple ion, but instead give more complex ion having complicated structure. For example, potassium ferrocyanide does not give the properties of K plus FeMC and negative ion, but give the properties of K plus ion and a complex ferrocyanide ion. Right. In other words, in this compound, the complex ion retain their identity in the solution, which is different from their constituents. Other example are hexammonia, cobalt, chloride, or we say potassium, BTCl6. They all are the example of complex compound which do not dissociate in water and keep their identity. So we can classify between the double salt, differentiate between the double salt and complex salt as they exist only in the solid state. In aqueous solution, they dissociate completely into the ion. Where the complex, they exist only in the solid state as well as in the aqueous solution, because the complex ion does not dissociate into the ions. Now, they usually contain two simple salts in equivalent proportion. The simple salt from which they are formed may or may not be in the equivalent proportion. They are ionic compound and do not contain any coordinate bond. They may or may not be ionic compound, but complex parties always contain a coordinate bond. The metal ions show their normal valency. The metal ion satisfy its two types of valency called primary valency and secondary valency. Later we are going to discuss in Warner's theory, right? Now, they lose their identity in the solution, they retain their identity in the solution. The properties of the double salt are same as those of their constituents compound. The property of this compound are different from its constituents. So these are the main difference between the double salt and the complex salt, right? Now, so let's see some terminology that use in the coordination compound. So if I'm talking about the complex ion, so a complex ion may be defined as the electrically charged entity which is formed by the combination of simple cation with one or more neutral molecule, or one or more simple anion, or in some cases positive group also. It exists as a single entity and usually indicated with the square bracket. So always remember, so complex ion are defined as the electrically charged entity which is formed by the combination of a simple cation with one or more neutral molecule, or one or more simple anion, or in some cases positive group also, right? So it exists as a single entity and usually indicated within the square bracket, right? Now, this is copper NH3 4 is in a complex ion which is formed by the combination of four neutral molecule of ammonia with a simple copper 2 plus cation. The complex ion carrying a positive charge, that is copper NH3 4 + 2, is called cationic complexes, and the one with the negative charge FeCN6 - 4 is called the anionic complexes, right? The one with the no charge, that is PtCl2 NH3 2, is called a neutral complexes. So always remember this. The copper NH3 plus 2 is a complex ion which is formed by the combination of four neutral molecules of ammonia with the simple copper 2 plus cation. And the complex ion carrying a positive charge is called cationic complexes. And the one with the negative charge is called anionic complexes, right? And the one with the no charge is called the neutral complexes. Now, what is homolaptic and heteroleptic complexes? So having only one type of ligand linked to the central atom, like here, only NH3 is act as a ligand in this complex. So it is known as the homolaptic complexes, where what is heteroleptic complexes have more than one type of ligand linked to the central atom. For example, here ammonia and chlorine both act as a ligand. So they are the example of the heteroleptic complexes, right? So always remember, complex ion do not give test for their constituent ions. We know that because they do not dissociate to give further ions, right? Because they does not give the test for copper plus and NH3. So always remember, complex ion do not give the test for their constituent ion because they do not decompose to lose their identity. They always retain their identity, right? Now, how will you represent representation of complex ion? So terms such as ligand, central metal, charge on complex ion, and coordination number can be illustrated as. So for any coordination complex, always remember this square bracket, right? This square bracket represent coordination sphere, right? This NH3 act as the ligand. This 4 represent the coordination number, or we say the number of ligand, right? This plus 2 represent the charge on the complex ion, and this copper represent the central metal ion, right? So you always represent like this only, right? So whenever you want to represent the complex coordination complex, always remember this point. Copper, which act as a central metal atom, NH3, which act as a ligand, and this 4 represent the coordination number, or we say the number of ligands surrounded by the metal, and the square bracket is known as the coordination sphere, and this plus 2 represent the charge on the complex ion. So this is how we can represent the complex ion. I hope this is clear to you, right? Now, for example, let me write, if I write FeCl 6 and this is -4, right? So Fe represent, what the Fe represent? This is central metal atom. This Cn represent ligand, and this 6 represent number of ligand. Number of ligand, or sometimes they also called coordination number. Both are correct. Coordination number, and this -4 represent what? This represent charge. Right? So these represent the charge on the complex side. So I hope this is clear to you. How will you represent the complex ion? Right now. So what is ligand? So basically ligand, as we know, and the name suggests, ligand is a lone pair donor, right? So anything which having lone pair of electron and they have a capability to donate this electron is known as ligand. So the central ion and metal ion is surrounded by the number of an ion or the neutral molecule, or sometimes positive charge ion possessing at least one lone pair. So it may be a positive, it may be negative, or it may be neutral. Doesn't matter. Just one criteria here, it having minimum one lone pair of electron. These surrounded ion are called ligands, right? The ligand are attached to the central metal ion or atom through coordinate bond or a dative linkage, right? So the ligand are attached to the central metal ion or atom through coordinate bond, or we say dative linkage. In the formation of coordination complexes, the ligand act as the electron pair donor, or we say Lewis basis, right? So in the formation of coordination complexes, the ligand act as the electron pair donor, or we say Lewis basis. Now, in the complex ion CuNH3 6 plus 3 and FeCl6 minus 4, NH3 and Cn are the ligand. Ligand invariably contain one or more atoms called donor atom having lone pair of electrons, right? So ligand invariably contain one or more atoms, or we also called as a donor atom having lone pair of electron. The number of donor group from a given ligand attached to the same central atom is called the denticity of the ligand. So always remember this, the number of a donor group from a given ligand attached to the same central atom is called denticity of the ligand. Like ligand like NH3, CH3, NH3 and PH3 can form only one coordinate bond with the central atom. So its density is 1. Now NH2, CH2, CH2, NH2. So we know that in this and having lone pair of electron. These and also having lone pair of electron. So they have a two donor atom in each molecule or ion, and each can form two coordinate bond with the central atom, and hence their density is also two. So we can say that their density is two. Here also now here and having lone pair and O also having lone pair. So in a one molecular ion they have a two donor group. So we can say that their density is two. Now on the basis of how many lone pair and a molecular atom donate, we can classify ligand as unidentate or monodentate ligand or polydentate or we say multidentate ligand. So what is unidentate or monodentate ligand? So these ligand contain only one donor atom or a site which is capable of donating an electron pair and thus attached to the central metal ion only at the one point like Cn negative, fluorine negative, chlorine negative, bromine negative, OH negative, H2O, NH3, NO2 negative, C2H5 9, that is pyridine, right? So these having the capability of donating only one donor atom. On the other hand side, polydentate or a multidentate ligand like ligand containing two or more such atoms which can simultaneously serve as the donor atom are called polydentate. For example, such ligand attached to the central atom ion at a more than one point. Right. Let's see some example. Polydentate ligand with the two donor site atom is known as bidentate, and with the three donor is known as a tridentate, and with the 4, 5, and 6 donor is known as tri, tetra, quadra, penta, and hexa. Right. So certain polydentate ligand have a flexidentate character. What do you mean by this term flexidentate character? It means they do not use all the donor atom to form a complexes like EDTA is a hexadentate ligand, but it can also act as a pentadentate or a tetradentate ligand according to the use. So they are the example of the flexidentate character, right? Now, some ligand like SO4 ion, etc., they can act both as a monodentate as well as the bidentate ligand. How? This is clear from the following example. So let's see some example. Like here, they act as a monodentate. How? Because here the SO4 only O can coordinate bond. The O will make coordinate bond with the CO. Thus, we can say that SO4 acts as a monodentate here only. Now here, these two O are act as a no donor group. So they here SO4 act as a bidentate. So some ligand like SO4 ion can act both as a monodentate as well as the bidentate ligand, right? So this we can explain. Right. Next is chelating ligand. So what is this chelating ligand? So basically a polydentate ligand, the structure of which permits the attachment of two or more donor sites at the terminal of the chain to the same metal ion simultaneously. Thus, closing one or more rings are called chelating ligand, right? So basically, chelating ligand, the ligand which provides the cyclic effect, right? When they have a more than two donor group, it will donate in such a way that they make a cyclic structure around the metal. So they are known as chelating ligand, or we can they develop chelation effect, right? So basically the polydentate ligand, the structure of which parameters the attach of the two or more donor sites at the terminal of the chain to the same metal ion simultaneously, thus closing one or more rings are called chelating ligand, and the compound formed are known as chelate compound, right? Thus, a chelate may be defined as the ring structure formed by the combination of a polydentate ligand having two or more donor atom at the terminal with the metal ion forming part of the ring. The process of formation of chelate is called chelation effect, right? So this is the formation, chelate formation. So chelate complexes are more stable than the ordinary complexes in which the ligand is monodentate. Always remember, chelate complexes are more stable than the ordinary complexes in which the ligand is monodentate. This increase the stability of the compound due to chelation is called chelate effect. Generally, the chelate complexes with the 5 or 6 member ring are more stable. Out of these 5 member ring are very, very stable when these involve the saturated ligand. Now, what is ambident ligand? So there are certain ligand which have a two or more donor atom, but in forming complexes, only one donor atom is attached to the metal ion. So they are having two donor group, two donor atom, but that's what ambident ligand are differentiate from the denticity. In case of denticity, what is happening now? If the any ligand having the two donor group, both these two donor group donating atom to the center atom. But in the ambident ligand, there are certain ligand which have a two or more donor atom. But in forming complexes, only one donor atom is attached to the metal ion. Such ligands are called ambident ligand, right? Then some example of such ligands are MnO2 like nitro, cyano, thiocyano, nitrito, and the isocyano, isothiocyano, right? So these all are the example of the ambident ligand. I hope this is clear to you, right? Good. So let me take some water till you just read this. I'm going to explain this as well. Okay. So what is bridging ligand? Basically, certain ligand like N2, NH2, NH2, NH2 negative, NH2 twice negative, O2, Cl, so 4 twice negative, NO2. They can act as a bidentate ligand when these are attached to the two separate metal atoms, right? And making a bridge between them. So they can act as a bidentate ligand when these are attached to the two separate metal atoms and making a bridge between them, right? So such ligand is called bridging ligand, and the complex form is given as the name as the bridging complexes, right? So this is known as the bridging complexes. Okay. Now, a bridging ligand must have at least two lone pair of electron, which the ligand used to get coordinate to the two or metal atoms. Like ligand having no lone pair of electron, that is a certain ligand having the lone pair of electron, but have a p bonding electrons, right? Pi bonding electrons. Such ligands are CH2, CH2, benzene, cyclopentadienyl, and etc. So these ligands have no lone pair of electron. Certain ligands have no lone pair of electron, but they have a pi bonding electrons, right? So such ligands are called CH2, CH2, benzene, and cyclopentadienyl. Now, what is central metal atom or ion? So every complex ion contain a metal atom or ion to which one or more neutral molecules or ion are attached. Right. This is known as the central metal atom or ion. It is sometimes also known as the nuclear atom. Right. So basically the every complex ion contain a metal atom or ion to which one or more neutral molecules or ion are attached. This is known as the central metal atom or ion. It is sometimes known as the nuclear atom also. In a complex, the central metal atom or ion behave as the electron pair acceptor or Lewis acid. Now, what is coordination sphere? So the central atom and ligand which are directly attached to it and enclosed in the square bracket are called coordination sphere. Right? We already studied this thing. The ligand and the metal atom shown inside the square bracket actually behave as a single constituent unit. The bonding between the central metal atom ion and the ligand in the coordination sphere is non-ionizable, right? It means it does not dissociate. The part outside the coordination sphere is called ionization sphere, or because this consists of ionizable ion which can ionize, right? Now, what is coordination number basically? So the total number of ligand attached to the central metal ion through coordinate bond is called coordination number. Remember this. The total number of ligand attached to the central metal ion through coordinate bond is called coordination number of the metal. Like in example, copper NH3 4 plus 2, the coordination number of copper is plus 4. Is 4. Why? Because as we can see that there is a 4 ligand which is around the central atom, right? So the total number of ligand attached to the central metal ion through coordinate bond is called coordination number. Okay. Now, in the complex ion, the coordination number of copper plus 2 is 4 and that of Fe plus 2 ion in FeCN 4 negative is 6. As we can see here 6 cyanide ion are act as the ligand which is surrounded the Fe atom. The coordination number of the most common metals are 4 and 6. Right. So the coordination number of most common metals are either 4 and 6. Ag plus Pt plus 2 Cr plus 3 Fe plus 2 Fe cobalt 3 and Pt4 and so only one coordination number. Like Ag show coordination number of 2 only. Pt plus 2 show coordination number of 4 only. Chromium, Fe and Fe3, cobalt and Pt show coordination number 6 only. In case of a polydentate ligand, coordination number is actually is equal to number of ligand into its denticity. For example, in this case, COBr2 EN act as a polydentate ligand, it having a 2 donor group. So coordination number with respect to Br is equal to T. Coordination number with respect to the En is equal to 2 into 2 because ethylene diamine, right? En is stand for ethylene diamine. They having 2 donor group. What is the structure of this? Like N is 2, CH2, right? So this is H2N, CH2, CH2, and NH2, right? So they have two donor group, one this and one this, right? So they are, how to calculate the coordination number. So coordination number with respect to En is equal to 2 into 2, which is equal to 4. So what is the total coordination number? The total coordination number here is also 6. So we can find the total coordination number as 6. So this is how we can actually find the coordination number. Now, oxidation number or oxidation state. So it is a number that represents an electric charge in which a metal atom or ion has or appear to have when combined with the ligand, right? So the oxidation number of copper in is copper NH36 plus 3 is plus 3, but its coordination number is 6, right? So the oxidation number of copper in NH3 is 3, but the coordination number is 6, right? So oxidation state means what? It is a number that represents an electric charge in which the metal atom or ion has to be appear to have when combined with the liquids, right? Similarly, the oxidation state of Fe is FeCN6 4 negative. So here the coordination number is also 6, but the charge is plus 2, right? But the oxidation state is plus 2 only because we know that FeCN. So you have to calculate the oxidation state of Fe, then it will take another X. We know the cyanide having the -1 charge, so this will be -1 into 6, 6, and this is equal to -4. So X comes out to be what? That is -4 plus 6. So X comes out to be 2. So X having plus 2 oxidation state, right? Now, what is this effective atomic number rule? So what do you mean by this term? Effective atomic number rule. So in order to explain the stability of the complex, Sedgwick proposed effective atomic number abbreviated as En, right? Which is defined as the resultant number of electron with the metal atom or ion after gaining electron from the donor atom of the ligand, right? So in order to explain the stability of the complexes, Sedgwick proposed effective atomic number abbreviated as En, which is defined as the resultant number of electron with the metal or atom or ion after gaining electrons from the donor atom. So how many electrons they have, right? So resultant number of electrons with the metal atom or ion after gaining electron from the ligands, right? The effective atomic number is generally coincide with the atomic number of next inert gas except in subgases. So this En generally coincide with the atomic number of the inert gases, like they are similar to the inert gas atomic number except in the subgases, right? So how will you calculate En? So we can calculate En like atomic number of the metal minus number of electron lost in the ion formation plus number of electron gained from the donor atom of the ligand. So this is how we can calculate. That is the atomic number of the metal minus the number of electron lost in the ion formation plus number of electron gained from the donor atom of the ligand. Let's see some example. For example, this complexes, if you want to calculate the En number for this. So how will you calculate? For example, here the atomic number of the metal is nothing but 27, right? Minus number of electron that will lose, that is oxidation state of cobalt here is nothing but plus 3. How? Because NH3 having 0 charge, Cl having minus 3. So this having the negative charge. Plus number of electrons gained by, for example, here 6 ligand of ammonia, this means 12 electrons, right? So 6 into 2, that is a 12 electron. So this is 12 electrons. So how will you solve? That is 27 minus 3. It comes out to be 24. 24 plus 12, that comes out to be 36, which is equal to which noble gases? That is krypton, right? Which is equal to krypton. Similar in case of K4FeCN6, we can calculate atomic number of potassium is not Fe is nothing but 26, right? Similar, the oxidation state is 6 and plus 4 of potassium, 6 negative, that is 2. So this will be 2 plus 12 pairs. So this is also 6 point 24, 24 plus 12, 24, 34, 36, right? 36, which is equal to again krypton, right? So this is how we can actually calculate. Okay, so this is the way to calculate the En atomic number, effective atomic number for the complexes, right? Now, what is Warner's theory? So let's we study some theories, different theories that were given by the three scientists, basically Warner and the VBT and the crystal field theory. So Warner proposed theory called Warner's coordination theory, for which he was awarded Nobel Prize in 1930. It was the first successful theory which explained the properties of the complexes. So this was the first successful theory which explain the properties of the complexes. So what the Warner's theory state? So basically, the main postulates of this theory are primary linkage, or we say valency, are ionizable and are exhibited by a metal in the formation of its simple salts such as a COCl3, COSO4, and AgCl. So in this salt, the primary valency of CO, Cu, and Ag are 3, 2, and 1 respectively. Nowadays, a primary valency is referred as the oxidation state of the metal, right? So the primary valency is referred to the oxidation state. So according to the oneness theory, the complexes follow two types of valency. One is primary and one is secondary. So primary valency is equivalent to the oxidation state of the metal ion. Similar, the secondary linkage valency are non-ionizable and are exhibited by the metal in the formation of the complex ions such as CuNH3 6 plus 3, CuNH3 4, and AgNH3, right? So in these complexes, the secondary valency of CO plus 3, copper plus 2, Ag plus 3 are 6, 4, and 2 respectively. The secondary valency is also referred to as coordination number of the metal, right? So we can remember like primary valency represent the oxidation state, where the secondary valency represents the coordination number. So these are the Warner complexes, that is COCl3.6NH3, and how modern, how will in later half, how will we represent this Warner complexes like CONH3 6 and the Cl3. So this CONH3 6, this represents the primary valency having coordination state, right? And they have a non-ionizable part where the Cl3 represents the ionizable part. Okay. So the ionization, upon ionization, it will convert it into this. So secondary valence is satisfied by 6 NH3 atom, where the primary valence is satisfied by the chlorine, 3 chlorine negative ion. On the similar basis, COCl3.5NH3 we represent as COCl and ClCl2. So 5 NH3 and 1 Cl negative. So secondary valency is satisfied by the 5 NH3 and 1 Cl negative, 3 Cl negative, including 1 Cl negative with a dual nature, right? So total 3 Cl and negative, including 1 Cl with a dual nature. So this is how we can represent the Warner theory. I hope this is clear to you. Now, the formation of coordination compound can be explained electrocally by the number of theories like a valence bond theory and the crystal field theory. So let's see the what the approach they use for the valence bond approach, right? So for the valence bond theory, VVT theory, what the approach they are using, the main assumption of the valence bond theory are the ions of the transition metal have the some incompletely filled d orbital. Some or all the electrons in the incompletely filled d orbital are unpaired as well. So it was suggested that sometimes the unpaired n-1d electron couple as fully as possible prior to the bond formation. In this process, some n-d orbital become vacant. Now the central atom does make available a number of empty orbitals equal to its coordination number for the formation of coordinate bond with the suitable ligand orbitals. Now, since the energy of the n-1 d orbital is only slightly less than that of s and p orbital of the nth orbital, right? These vacant orbital mix together to form a new equivalent orbital called hybrid orbital. So always remember, since the energy of the n-1 d orbital is only slightly less than that of s and p orbital of the nth orbital, thus they have a vacant orbital mixed together to form a new equivalent orbital called the hybrid orbital. Each ligand has at least one lone pair of electron. The hybrid orbital formed take part in the formation of hybrid bond with the ligand by overlapping. The bond formation takes place by the accepting the lone pair of electrons by the hybrid orbital of the metal and from the ligand. Especially the orbital that would be used for a metal ion of the first series are the two 3d, one 4s and three 4p orbitals, right? So especially the orbital that would be used for the metal ion for the first series, that is the two 3d orbitals, one 4s and three pv orbitals, right? The rest 3D or inner orbital on the metal ion do not participate in the bonding. When n-1 d orbital are used in bond formation, the complex formed are called inner orbital complexes. Sometime in place of n-1 d orbital, outer nd orbital are also used for the hybridization. Then they are called the outer orbital complex. The bond hybridization involved and the resulting geometrical shape of the complexes are given in the following list, right? So this is how if the coordination number of 6, we have a three diff cases. Either we have a hybridization D2sp3 or sp3d2, right? So either we have a hybridization D2sp3 or sp3d2. So in case of coordination number 6. Similar in the case of coordination number 4, we have a two different hybridization, either sp3 or dsp2. Okay. So let's see. For example, so if the bond hybridization D2sp3, then the geometrical shape is nothing but it will be octahedral, or we say inner orbital complex, because in this inner d comes into the picture, right? So the d orbital use basically a dz square. So which d orbital you are using in the inner orbital complexes, that is dz square. This thing become clear when we study the crystal field theory, right? Now, and the typical example is FeCl6. Similarly, sp3d2, these octahedral ultra complexes, and basically here, wait, this will be happening on the case of outer orbital complexes in case of weak ligand as well. So here the d orbital use are dx square y square and the dz square. So always remember dx square y square and dz square. So here the F is F6 3 negative. Similar sp3 and dsp2. So sp3 having the shape tetrahedral and dsp2 having the shape square planar. So these are the examples. Now, so this is all about the VVT theory. So let's do some questions related to VVT theory so that you can understand this thing as well, right? So let's see some question, and after this we're discussing some PYQ question as well. Right. So, for example, by using VVT theory, if you want to actually predict the shape of the following complexes, then how will you predict beta? Right. So, how will you predict the shape using the VVT theory? Right. So, let's see how will you predict the shape. For example, if we have a complex like K4 FeCl6, right? If we have a complex like K4, and this is nothing but FeCl6, right? K4FeCl6, and someone wants to calculate the magnetic character, or we say the basically the what their shape, hybridization, all these things. So we know that here one important note here, coordination number is 6. So it indicates that the structure is nothing but octahedral, right? Octahedral, right? So this is octahedral. So in step 1, always calculate the oxidation state. So step 1, always calculate oxidation state. So here, what is oxidation state? So oxidation state of Fe is nothing but how will you calculate beta? Oxidation state of Fe is nothing but this have a 4k. So we have a 4 into 1 plus x minus 6 is equal to 0. So what x comes out to be? That is 2. Right? The oxidation state of x is 2. So we can say that here Fe is in plus 2 state. We know that what is the electronic configuration of Fe plus 2. So we have know that that is 3d6 because in Fe having electronic configuration 3d6 4 is 2. So in plus 2 state they're having 3d6, right? So this we also know. Now the next important note here, you have to identify the ligand. You have to identify the ligand, right? So how will you identify the ligand beta, whether it is a strong ligand or a weak ligand? So how will you identify? So basically, as we can see that Cn negative. So the Cn negative is the strong ligand. Always remember, we have a spectrochemical series for CFT theory. So from there also we can remember. So these are the strong ligands, right? So these are the Cn negative is nothing but a strong ligand. So what is happening in the strong ligand now? In case of hybridization, right? So in case of hybridization, how will you actually draw this? So we know that in case of hybridization, we can draw this as this is nothing but like uh let me draw the orbital picture. So this is 3D 4s orbital and this is 4p orbital, right? So this is in ground state. So we know that d orbital having 5 orbitals, 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, and here 6 electron, right? These orbitals are empty. Now, what happening in excited state since the ligand is strong? Always remember when the weak ligand, then the above picture is very, very correct. That is this electron pairing is very good. Now, if the ligand becomes strong, then we know that this 6 electron we have to fill like this. How? That is 1, 2, 3, 4, and this is 5. Right. So these that is how we have to fill the electrons if the ligand is strong. If the ligand is strong, then pairing will take place. So these 2 electrons get paired to form this. Okay. So now this s orbital is empty. This p orbital is also empty. So we have a 6 ligand. So one ligand comes to this, and this. So what the structure basically is, that is nothing but D2sp3, right? So the shape become D2, hybridization become D2sp3. So the first thing is very much clear, that is hybridization using BBT theory. So hybridization comes out to be D2sp and 3. Now, the second most important thing is whether it is a paramagnetic or diamagnetic. So if there is no unpaired electron now, it means it is a diamagnetic, right? So diamagnetic. So it is diamagnetic in nature. Always remember this. Okay. So the first hybridization, that is D2sp3, and the next is it is a diamagnetic. Okay. Now what's the next thing, beta? The next thing, that is hybridization, that is diamagnetic, and the next thing is if you want to calculate the inner orbital or outer orbital, which complex they are. So basically in this, the inner d electron, that is 3d. So these d orbitals are used now. So they form inner orbital complexes. So they form inner, also known as inner orbital complexes, right? So they form inner orbital complexes. Now next is important. They also known as a high spin or low spin. So low spin complexes. Why they are called low spin complexes? Because in this unpaired electron is very less, or we have zero unpaired electrons. So they are known as low spin complexes. Those having the maximum number of unpaired electrons are known as high spin complexes. So from these question only, you can predict this 4 points. That is their hybridization, their magnetic character, whether there is a para or dia, their inner orbital complexes, low spin and high spin complexes, right? So I hope this is clear to you, right? Now we study, that is crystal field theory. Okay. Now, before studying crystal field theory, let's look some the orbital diagram of d block elements. So we know that d orbital having five orbitals, right? So out of these five orbitals, dxy, dyz, and dzx, right? So dxy, dyz, and dzx. And the another set is dx square y square and dz square, right? So d orbital having having the five orbital, d subshell having the five orbital. Out of these three, these are lying along the between the two planes like xy plane, yz plane, dz plane, and these are lie along the axis of the along the axis like x square, y square axis, and z square. So this is known as T2G, and this is known now term as EG, right? So basically, here what is happening in absence of ligand, they all have a equal energy, so their degeneracy is present. As the ligand come, their degeneracy is lost. What is happening basically? These five orbitals. It is let me write this five orbital as uh, d orbital having five orbitals like one, two, three, four, five. Right. So this is in case of absence of ligand. So this is in case of absence of ligand. As soon as ligand comes into the picture, so this is in absence of ligand. Let me write absence of ligand. They all having same energy like dxy, dxy, dz. Now, if the ligands come, so if the ligands comes into the picture, the energy of all these five orbital will increase, or we say their G generosity is lost. However, the energy out of these five, some having higher energy and some having the lowest energy, right? So those having the highest energy, like these two orbital, they are termed as each, and those having the lowest energy are termed as T2G, right? So in absence of ligand, and they are in presence of ligand. So these are happening absence of ligand and presence of ligand. So in presence of ligand, their degeneracy is lost, and they all having some equal energy will be increased. Now the energy increase is different. Like in EG, the energy increase is more than T2G. The energy increase is less. Why there is more energy increase in the EG orbital? Because these orbital lie along the axis, and when the ligand come, the repulsion takes place along the axis is more. Right. That's why their energy increases. So this is the energy order. Right, this is the energy order. This is splitting energy is known as octahedral splitting energy. Right, this splitting is known as octahedral splitting energy. So in T2G we know we have a three orbital like dxy, dyz, and dzx. In EG we know that we have a two orbital like dx square, y square, and dz square. Right. So we have a three different orbitals, dx square, y square, dz square, and these three. Right. So this is how we can actually draw the diagram for the crystal field splitting theory. Now, one important note here. Now, this is the two orbital. So this is a hypothetical known as a barycenter. Right. This is a hypothetical center. So if they have a energy increase, for example, they have an increase for zero point 0.6, because in this EG we have a two orbital. So if they are the zero point 0.6 amount, and then this have a -4 in negative amount. So -3, 4 into 3, that is 1.2, and 6 into 2 plus 1 by 2. So the net will become 0. So this is how we can actually calculate. Okay, now important thing here, how to calculate CFSC basically. So in case of always remember this thing because this is very important. Now, what happening? We have a two case. If delta O is more than the pairing energy. Then how will you write the electronic configuration of D4? Let me draw the diagram. We know this. This having T2G and this having EG. Right? This having EG. So I'm saying that in this delta O is more. So if the delta O is more, right? So if the delta O is more, the large energy difference, then how will you write D4? D4 like 1 electron, 2 electron, 3 electron. These 4 electron, whether they are placed in EG or again T2G, it depends upon how much energy difference between the T2G orbital and the EG orbital. So if the energy difference between the T2G orbital and EG orbital is less, then definitely this fourth electron will placed in the EG orbital, right? Now, if the energy gap is very much high, that is splitting energy is much more, then this 4 electron will place into the T2G level itself. So we can say that in this case, how can you predict the hybridization and all this thing? So the hybridization become nothing but it will become, yes, it will become D2sp3, the first one. Which D2sp3 beta, which d orbital comes into the picture? So here, which d orbital? That is dx square y square and dz square. So these two orbital are, vacant. So these two orbital take place in a bond formation. So dx square y square dz square what takes place in the. So if someone asks in D2sp3 which d orbital will take, so we'll say that dx square y square and dz square. So these two orbital are basically takes place in the bond formation. I hope this is clear to you. Now, is there any unpaired electron? Yes, there is the two unpaired electrons. So we can calculate the magnetic moment as well. So the magnetic moment is nothing but under root n, and this is n plus 2, right? So we can calculate the magnetic moment as well. Okay. How? Like this is mu and this is under root n plus 2. So what we then here? A number of unpaired electrons nothing but 2. So we can calculate 2, 2 plus 2. 2 to the 4, 4 to the under root 8. Like 2 point something. Right. So this is how we can calculate angular momentum as well. Now in case 2, what happening if octahedral splitting is less than the pairing energy, then how will you draw the diagram? Then we'll draw the diagram like now their splitting is very much less. Okay. So this splitting is less. So if the splitting is less, then how will you fill the 5 electrons? The first electron 1, 2, 3. Fourth electron, whether it go into the T2G or EG, it depends upon the splitting energy. Here, splitting energy is less. So this 4 electron obviously fill in the upper level, that is 4 and 5. Right. So this is how we can fill. So here, if someone asks which d orbital will takes place in hybridization, so here the hybridization become sp3d2. So which d orbital is used here? So basically the outermost d orbital that we are using in this, right? Not the inner d orbital. So they will form outer orbital complexes. So they will form outer orbital. In the above example, they are from inner orbital complex. So they form outer orbital complexes. And here we can observe it will form high spin, right? Because spin is very much more number of unpaired electron is there. So it also form high spin complexes. So I hope this is clear to you, right? So this is the two possibility in the CFT theory that how we'll actually draw the diagram. Now let's discuss some question. This is a previous year question that were coming in your examination. So let's discuss some question. It's to really help you to understand the entire topic in a better way. That is which type of question they generally ask you, right? Okay, so let's see. The first question is what? In this question, they are asking match each set of hybrid orbital from list 1 was complex given again list 2. For example, In DSP2, we have SP2, right? So list one, we have a R, Q, RS, and list one, we have a FEF, right? Okay? So you have to just match the following with the correct one. Okay. So we know that FEF6, 4 negative. So they're having a shape either D2sp3 or sp3d2, because in octahedral we have only two possibility, d2sp3 or sp3d2. For this you have to identify the ligand. If the ligand is strong, if the ligand is a strong ligand, then it will form d2sp3. If the ligand is weak ligand, then it will form sp3d2. So we know that F is a weak ligand, right? What is the series for remembering the ligand name better? That is this one, spectrochemical series. So just remember. Okay. So we can observe that is Cn and Cu are the strong ligand and these are the weak ligand, IBrCn, right? So F is a weak ligand. So definitely the shape is sp3d2. So the first one is sp3d2. That is one is equivalent to R, right? So one is equivalent to R, sp3d2. Okay, so one is equivalent to R. So try to identify here R is equal to 2, R is equal to 3, R is equal to 1, R is equal to 1. So these two options is neglected. So only these two. Out of these two, you have to select. Now, in this one, a titanium S2O3 and Cl3, right? So both S2O and Cl3 both are the weak reagent. And in this case also they have a titanium. So this will also form 3 and 3 6 sp3d2, right? So 2 is also equivalent to R is equal to 1. So this 2 is also equal to S. Like whether it will form D2sp3? No. This 2. Right here, titanium S2O3 and Cl3. So let's find the oxidation state first. So if you find the oxidation state of this, then how will you find this? Like titanium having +3 oxidation state, right? So in +3 oxidation state, what the titanium? Basically, titanium, that is titanium in +2 oxidation state, it is 3d2, right? So titanium in +3 oxidation state, they will become 3d1, right? 3d1. So 3d1. So according to the this theory, 3d1, how will they fill this? This will be like this one CFT theory. Okay, so only one pair electron they having. So they have only one unpaired number of electron. So their shape is D2sp3 because this d orbital is empty, right? This d orbital is empty in this case. So the shape is D2sp3. So for 2 having equal to S, so 2 having equal to S, so we can write 2 is equivalent to S. So here also S is equal to 2, S is equal to 3. So this is incorrect. So only correct option is C. So by just solving the two points, we get the answer. Like C is the correct option for this, right? So this question is totally based upon the CFT or VVT. By using any of these two theory, you can solve this question. Now, next question, that is question number this one, right? What the question asks beta in this question, what they are going to ask you. So they are asking, choose the correct statement among the following. FeCl has a tetrahedral geometry. So yeah, this is absolutely correct because in coordination number 4, we have a two different shape, just like a coordination number 6. Like either will be sp3 and will be dsp2. So when will be sp3? When the weak ligand is present. And when the strong ligand is present, it will be dsp2. Right. So we know that Cl is a weak ligand, so having geometry tetrahedral. So whenever the sp3 means tetrahedral, tetrahedral, and the DSP2 matlab square planar, a square plane. Right. So this is square planar. So we can easily identify FeCl4 has a tetrahedral geometry. So this is absolutely correct. So this one is correct. Now, FeCl, let's move to the third one directly. FeCl4 negative has a higher spin magnetic moment than this. Obvious, because we know that in case of weak ligand, there no pairing takes place. So we already understand this thing. If the ligand is weak, if there is no much pairing, then they have a high spin. Right. So high spin means a more number of unpaired electron. So this is absolutely true. Now, the cobalt ion in the complex, this has a sp3d2 hybridization. So in this, NH3 due to the a strong ligand due to presence of En and NH3 strong ligand presence, they having a D2sp3 hybridization. Right? They having a D2sp3 hybridization, not sp3d2. This is wrong. Now CON and NH3 Cl2 has a two geometrical isomer. This is also wrong. So what is the correct option for this? A and C. Right? CO and NH3 has not two geometrical isomerism. It having a three geometrical isomerism. Right? So they having a three geometrical isomerism, not two. Right. So the correct option among the following is only A and C. Okay. The next question is, you have to calculate this, right? Like for the octahedral complexes Fe3 and SCN thiocyanide and in CN ligand environment differences between the spin only magnetic moment in Bohr magnetism when exponent to the nearest. So you have to calculate in both the cases. We know that in case of Fe and here SCN negative. Okay. So FeCN6 and this will be -3. And similar in case of cyanide. So this is FeCl6, right? -3. Here also -3, na? Good. So in both cases, Fe having oxidation state of +3. But what the difference in both this? Because here the Cn is a strong ligand. So in case of a strong ligand, the splitting energy is very much more high, right? If you draw the diagram, we get like this. This is called T2G and this is called EG. So energy gap is very much. So how will you write the 3d6? We know Fe plus 2, we have a 3d6. The Fe plus 3 having 3d5. Right? They're having 3d5. So one electron, two electron, three electron. This four electron, whether it go upwards or downwards, it depends upon the splitting energy. So here the splitting energy is very much more because the Cn is a strong ligand. So this is 3, 2, and this is 4, and this is 5. Right. So they have only one unpaired electron. So n is equal to 1 only. But in case of this SCN, since this is a weak ligand, so here this splitting energy is very, very less. Splitting energy is very, very less. So the 1, 2, 3, and 4th and 5th electron move upward. So here n is equal to 5. So number of electron is equal to 5. So how will you calculate the spin magnetic moment? It will comes out to be under n plus 2. So 5, 5 plus 2. Right, 5, 5 plus 2. And in this case, it will equal to under root 2, 2 plus 2. 2 to the 4, 4, 8. This is under root 8. So in this, it will be equal to 5, 5 to the 7, and 35. 30, 36, we know that the root of 36 is nothing but root 6. That is almost 6, right? 5.90. And it 93, it is almost 2, right? 2 p 2.90 p. So we'll subtract this is 6 minus 3, that is 6 minus 2. It will comes around 4, right? So this comes out to be 6 minus 2, which is equal to 4. So this is how we can actually write. Here on one page is only one now. So this is n plus 1 plus 2, that is under root 3. So under root 3 here, this will come as under root 3, or we say 1 point something 73. So this is 4 minus 6 minus 2 is equal to 4, right? There's correction. There's only one electron is there. So how will you calculate the magnetic moment? It will be like n plus 2. So here n is only 1. So it will be 1, 1 plus 2, that is 3. So under root 3 means nothing but 1.73 or assumed to be 2. So if you subtract 6 minus 2, we get the 4. Right? So this is very simple question, and this is again based upon the crystal field theory itself. Now, the next question. Among the species given below, right, among the species given below, the total number of diametric species H atom, NO2 monomer, O2 superoxide, diametric sulfur vapor phase, Mn3O4. So you have to identify the this one, right? So the paramagnetic, which one of the paramagnetic is basically paramagnetic, like HNO2 is a paramagnetic. Monomer O2, that is super, we already know that is a superoxide are paramagnetic in nature. So this is superoxide. H2 in vapor phase, they are also paramagnetic. And this is Mn3O4 is mixed with the oxide of Mn2 plus. This will also form. So among the species given the total number of diamagnetic species is only one. Which one? That is K2CrO4. So only this one is diamagnetic. So the correct answer is only one. Right. So only one is diamagnetic. Now, this question is also very, very important. Consider the following complexes ion P, Q, and R. P is equal to Fe6 and Q is equal to this and R is equal to this. The correct order complex ion according to the spin only magnetic moment. So again, you have to calculate the spin magnetic moment. So we know that in FeF6, right? Fe having +3 oxidation state and they having weak ligand. So they have N comes out to be 5 in this case. We already draw this thing, right? I need to draw again. Okay, let me draw this thing again. We know this thing in case of this, since F is a very weak ligand, and here Fe having +3 oxidation state. So they're having 3d5, right? So 3d5, how will you write 3d5? Like this. So having 1, 2, and 3. Since the ligand is weak, so this splitting energy is very less. So this will write as 3, 4, and 5. Right? This will write as 3, 4, and 5. So total N we have a 5, right? So here N is equal to 5. Now in vanadium H2O6, since +2. So here vanadium, that is science teacher very. So science teacher very. Vanadium in +2 form, it having science teacher very. That is 3d3. Right. So here the oxidation state of vanadium is what? That is +2. So in +2 they have a 3d3 form. So they have only 3d3. So only a 3 ampere electron. So N is equal to 3 only for this case. Now FeH2O6. So in H2O6 +2. So they have a Fe +2. Fe +2 means they having 3d6. Again H2 is the weak ligand. So 1, 2, 3, 4, 5, 6. They have a 4. So N is equal to 4 here. So maximum number of unpaired electron present in the first case, that is in P case. So P having the maximum, spin magnetic moment. So P having the maximum. After P, we have N is equal to 4 like R, and minimum will be Q. So the correct answer is like this. P minimum will be Q, then R, then P. So the correct option is B, right? So the which option is correct? That is the B option. So I hope you'll get the idea that how will you solve the question related to this. Okay. So this is how we can able to solve the question related to this chapter only, right? So just if I'm talking about the coordination chemistry and the transition elements, just try to focus on the important things of the DNF block elements, and in coordination complexes basically try to solve questions on VVT theory, CFT theory, spin magnetic, and it is the optical isomerism. So these all are the important topics of this chapter. So if you know the concept of this VVT theory, CFT theory, and all these things, then you can easily solve this question. No problem. You are not facing any problem related to this questions anymore, right? So I hope this is simple to you. Now, let's do one question more. So the geometry of the ammonia complexes in Ni2 plus, Pt plus, and Zn2 plus respectively. So now the geometry they are asking. So with the Ni +2, right? So Ni and this will NH3 6, and they having the +2 charge. So they will form in +2 oxidation state. So it will form the NH3 is a strong ligand, right? So it will form the octahedral. We know that whenever this will 6, this will form octahedral. So this is the octahedral in case of this. Now similar in the platinum +2. So in case of platinum +2, this will form with only 4 coordination number, right? That is +2 form. So this is nothing but this is known as square planar, right? So it will form a square planar. Square planar. Similar with the Zn +2, they will form Zn, NH3, this is 4, and this is 2 plus, right? So it will form tetrahedral. So the correct option for this question is A, that is octahedral, square planar, and the tetrahedral. So this is how we'll be able to solve this, right? So I hope this is clear to you. No problem in this. No, you have no doubt related to this. Okay. So this is all about the today session that we are discussing already ABVT theory, coordination complexes, some block elements, and also do some question on the advanced level, right? So these questions were from previous advanced paper. So try to solve the questions by understanding the concept. You can able to solve the question, no problem, right? So this is all for today. Let's meet in the next class where we'll discussing some new chapters. Okay, so this is all for the today. Thank you, and let's meet on the next class.